case you have one bin and then you want to figure out what the bit duration of each bit is. That would just be more or less 1 divided by 2000, right? So in a way, you can say bit interval is usually the inverse of the bit rate. So given the bit rate, 1 over that, which is the inverse of it, will obviously give you the bit interval. So in this case, 1 divided by 2000 seconds, which gives you 0.0000500 seconds, which in other words can be shown as 500 microsecond. That's 500 microseconds because it's 6, right? Micro is 6, 10 raised to the power 6. That's 1, 2, 3, 4, 5, 6. So 500 microsecond. So to note, you can say bit rate and then the bandwidth are proportional to each other. Okay, so to note, bit rates are proportional to each other. That's bit rate and bandwidth. I want to look at another part, another component of transmission, which relates to channels that digital signals or signals passes through. And I want to look at it from baseband transmissions and what roles they play within some of these implementations when it comes to transmission in general. Okay, so baseband transmission, looking at digital signals over a medium or a channel. So at the analog level, or okay, so we're going to look at baseband transmissions from both analog and digital level. And we've already looked at this for the representation of analog and digital signals. Analog taking a sine wave format, whereas digital taking a discrete, more or less with discrete state and value as well. It's either high or low in this representation. So for information to be converted back and forth, for signal to be converted back and forth between the analog and digital, because it forms a huge part of how transmission takes place. Obviously, not every signaling uses binary. Some signaling falls solely on analog, and if we wanted to have it in a digital form, there has to be a way to handle conversion. So this is where the telcos do a pretty good job with various devices like modems to help us do the conversion between analog and digital signaling. So a telco will give you a modem. A modem is designed to basically handle the conversion between analog and digital transmission. So your computers would have the digital side, whereas the analog will be the main information that comes through from the telco. So for a telephone network, that's how it would be structured, where it goes through these various mediums, and it's the job of the end-to-end modems to help with the conversion back and forth. Low band and band passes are key frequency channels that are used to read signaling within transmission. So I want to look at some of these and what kind of characteristics that goes with it. Okay, so for uh, low pass channels, you'd have frequency that ranges from the start of the time to a given frequency state, whereas band pass channels can have frequencies start from any other point and end at a different point. So the change within the two frequency time slots will determine how the frequency is being managed or allocated for a given transmission. Okay, so key emphasis over here is on the frequency states in terms of either it's whether it's starting from starting from a 0 point or it's starting from just an initial or starting from a different predetermined frequency point to a given frequency point. Okay, and that applies for the base band, whereas the low band is more of it's starting from an initial point. So in general, you say that low pass channels do start directly off the amplitude from a 0 and ends at a given frequency that's been allocated to it. Whereas band pass channels can start from any frequency uh, level and end at any frequency level as well. So calculation wise, trying to put this into a calculation point so we can easily identify how some of these concepts play a role in transmission of information. Looking at it from power point of view, because power is quite essential in how the uh, uh, some of these signalings takes on various channels within a given frequency to address low pass and band pass uh, transmissions. So one question here a question that you probably face within some of these concepts here is if suppose you had a signal travel through a transmission medium and its power is reduced to one half, meaning that the meaning that uh, the the earning power is actually half of what the starting power is in terms of its frequency channel representation. So that's what it means. It says that means that uh, the end power, the the end power is usually it's half of the starting power. So it means the power that was actually that a signal traveled with at the initial state uh, is at it's halved when it gets to its um, uh, peak point or uh, destination point. Because we want to look at the loss of power, which is the attenuation part. So that's where you look at attenuation within the signal when when there's a variation between the starting power and an ending power, then we'll talk about attenuation. Okay, so loss of power. We want to figure out how to calculate that basically, and there are formulas that are used to handle that. The formula for calculating loss of power is 10 times log base 10 of the finishing power level divided by the starting power. So within this question here, we're told that the uh, uh, the signal traveled through a transmission medium and its power is reduced. So meaning that the uh, when the signal ended, it actually had half of the initial power that was transmitted. So it means that P2, if we're to plot in a graph, P2 is half of P1. And using the attenuation or the loss of power formula, which is 10 times log base 10 of uh, the ending power divided by the initial power. If you were to plug the values in there, you'd probably end up getting this value here. And the way to go about that is obviously stated clearly that half of the initial power was received at the ending power, at the final state of the power. So it'd be 0.5 of P1 divided by P1 is divided by P1, taking the log base 10 of it times 10 will give you the attenuation or the loss of power. Okay, so if you're not conversant with logs, it's actually a bit simple if you've done a bit of um, math. I think I'm hoping some of you have already covered some of your basic college math when it comes to logs or logarithms within either trigonometries or basic or algebraic um, mathematics. So either trig or algebra should give you some of these concepts. So anyway, generally log to the base of any value of a log to the base of any value of a given number is termed the log value raised to the power what will give you that particular value. So in this sense, uh, looking at the calculation, P1 will cancel out, leaving only 0.5. So we're saying 10 times log base 10 of 0.5 is what the calculation is. And to determine log base 10 of 0.5 is just saying that 10 raised to the power what will give you 0.5 or half. And if you do the math very well, 10 raised to the power 0 is 1. We are looking for half or 0.5. So which means we have to go to some negative values. If we're to go with 10 raised to the power minus 1, we'll probably get, using a calculator, should get about minus 0.75 something. So obviously minus 1 wouldn't help. 10 raised to the power minus 1 wouldn't, 10 raised to the power point, 10 raised to the power minus 0.1 wouldn't do the trick. If you plug into a calculator, you should realize that 10 raised to the power minus 0.3 actually gives you the 0.5. It's actually 0.50 something if it's to plug into your calculator. Okay, or I think it's 0.51 or so. So to run it off is just 0.5 basically. So which means uh, the value of 10, so log base 10 of 0.5 is actually minus 0.3. And that minus 0.3 times 10 will give you minus 3 decibel. So power is obviously measured in decibel within a signaling transmission. Okay, for a given transmission, power is measured in decibel. Okay, so you say that a loss of 3 decibel, which is the same as minus 3 decibel, is equivalent to losing 1/2 of the power. So that's how we're able to derive the attenuation or the loss of power for this particular uh, signal traveling through a transmission medium and having half of the of its power at the finishing end of from its starting point. Okay. Another calculation would revolve around something like, say, sometimes the decibel is used to measure signal power in milliwatts. Okay, so sometimes the decibel is used to measure signal power in decibel, in milliwatts. So in a case where you'd prefer to have decibel in milliwatts, then if we're to calculate the loss of power, let's calculate the loss of power, then the formula also still stands the same, and it will be 10 times log base 10 of the power in milliwatts. So where P is, well, obviously pi milliwatts. To calculate, so if you understand this concept very well in terms of how signal power being measured in milliwatts, uh, in terms of computation, if you do get the concept straight, then what would happen if we were to calculate the power of a signal with a with an attenuation or a loss of power of a minus 30? And here, this application of the formula can give you the answer pretty straightforward. So we're saying that um, uh, the power, either loss of power or whatever power it is, in decibel equals 10 base 10, so 10 times log base 10 of the power itself. We're trying to calculate the power that will give you the lost part uh, given. So in this case, we've been given the power of the signal already, whether it's a lost power or 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 just the power itself, whether it's lost or not. They told you it's minus 30. So plugging that into this formula, we say that minus 30 is this. So in that sense, we want to calculate the actual power that led to that minus 30 in terms of power loss or attenuation. Now, before that, we were calculating the attenuation, the same formula, and we got this. We got minus 3 to be the power loss, right? But in this scenario over here, we want to actually calculate the actual power itself from uh, from initial point to the ending point, given the either loss of power or the power that was uh, calculated, or that was basically derived from that particular transmission. Okay, so let's plug in the values and see whether we can get the appropriate numbers. So you do have your formula, you have your power, you have your power lost in milliamps, and so in milliwatts, right? So which is minus 30. Minus 30 equals 10 times log base 10 of the initial power of the power transition between its initial state and then the ending state. And that's what we need to find. We need to find what power was actually used to derive this power loss in milliwatts. Okay? So We can for this we have to can divide the 10 on both sides, which will make that which would change the power to -3. If you were to divide it by 10, you divide -30 by 10, you'd have 3 left. So now the question is, um, look, applying the laws of log, 10 raised to the power -3 should give you this value, right? 10 raised to the power -3 should give you this value. So you can plug that into your calculator. You'd obviously get the answer to the actual power that was used to derive this, actually that was used to determine this either loss of power or attenuation level of the particular signal transmission. Okay, you just got to know your log calculations and understand what exactly has been expected from the question, given the actual formulas that you'd have. So the key, I mean, this scenario over here, when it comes to the low band and band pass, it's more of the 10 times log base 10 of the ending power divided by the initial power. And this will form the power that will help you calculate attenuation. And attenuation can either be loss of power or not. So which can determine whether power was lost or not. Okay, so once you do have this formula in hand, then the rest should be pretty easy. You just substituting the values into it to give you whatever um, missing variables that you need to calculate for. Okay, so in this case, we're actually calculating the power that gave us the attenuation level of -30, and it was pretty straightforward calculation. Okay, data limits. A very important consideration in data is communication and how it affects uh, the data rate or the rate at which the data flows within a given medium. So let's look at data rate limits. Okay, and just a brief view, so we can go to understand uh, its forms of calculations that goes with it, or the type of theoretical concepts that goes with data rate. So data rate limits, a very important consideration in data communication is how fast we can send data in bits per second over a given channel. Data rate depends on three main factors: the bandwidth available, the level of the signals we use, and the quality of the channel, which is the level of the noise. So if you have bad noise on a given uh, signal, it would obviously affect the data rate. Okay, or in other words, it would affect the quality of the channel to be able to address your data rate limits. Okay, and to address some of these, there are a couple of theories that have been implemented to help us uh, kind of like zone in on some of the data rate limitations that we do have, or to be able to address and be able to solve the uh, data rate issues. One of them happens to be the noiseless channel, which was derived from Nyquist, from a Nyquist bit rate. The Nyquist bit rate was was a theory that was defined by a guy named Nyquist, and he stipulated that if signals or data transmission within a given medium has uh, limitation in the transmission, then we can look at the noise point of view to help us identify how it shapes the rate at which the data is being transmitted. And it's obviously a theory that was highly recommended, and it helped address data rate issues or bit rate issues in general, but obviously relating to data rates. So Nyquist's theory, which defines the theoretical maximum bit rate for a noiseless channel. So Nyquist is the guy that pretty much came up with the theoretical concept behind noiseless channels. They go to address issues that relate to bit rates or data rates limitations. His theory came up with a formula which states that bit rate equals 2 times the bandwidth times log base 2 of the signal level. So L here is the signal level, that's we pointed over here, the level of the signal. So 2 times the bandwidth times log base 2 of the signal level will determine the bit rate. So in a scenario where you do have the bandwidth, you do have the signal level as well, then you should be able to calculate the bit rate. And if you did have the bit rate and you were asked to either calculate the bandwidth or the signal level, you should be able to uh, go through the calculation very well. So I guess what I'm trying to say is if you had a situation where you were given the bit rate as well as the bandwidth, you should be able to calculate the signal level. Or in another form, if you do have this bit rate as well as the signal level, you should be able to calculate the bandwidth that's required for that particular transmission medium in terms of noiseless channels. So keep that in mind. This applies to most noiseless channels. So an example, calculation wise, let's consider a noiseless channel with a bandwidth of 3000 Hertz, transmitting a signal with 2 signal levels. So they've given you the key variables that you need, and they ask you to calculate the maximum bit rate. So in this case, if you go to go back, you've been given the bandwidth of 3000 Hertz as well as the signal level of what 2 signal level. So the answer to derive the bit rates, you just take 2 times 3000 times log base 2 of 2. So I'll probably say um, log base 2 of 2 be 2 raised to the power what will give you 2, right? So that's how you look at it from 2 raised to the power what value would give you 2. And my guess is if I'm to use my calculator, let me see if I can get that real quick. So 2 raised to the power 2 raised to the power 2 gives you 4. We need 2. So obviously, let's say we're to use 2 raised to the power 1. That should give you what? 2, right? Because 2 raised to the power 1. 2 raised to the power 1 is obviously 2, right? So with that, um, I should have even guessed that right away. What 2 raised to the power what will give you 2? It's just 1. Yeah, I'm getting tired, and that's probably the reason why I couldn't think through that easily, quick enough, or yeah, quick enough. 2 raised to the power 1 is 2, right? 2 raised to the power 0 is 1. So 2 raised to the power 1 is 2. So it means that the log base 2 of 2 is 1. 1 times 3,000 will be 3,000. 3,000 times 2 is 6,000. So in other words, the bit rate will be 6,000 bits per second for a noiseless channel. So for this question, the answer to your bit rate will be 6,000 bits per second. Exactly. So 6,000 bits per second. Okay. How about another question? Uh, Considering uh, the same noiseless channel, transmitting a signal with 4 signal levels. For each level, we send 2 bits. What will be the maximum bit rate that can be calculated? So this is a pretty good question, which is just like this right here. It's about the same as this. Um, so in with this one, the going by the formula, it would be, let's go by the formula again. It will be 2 times the same 3,000 piano that we had times log base 2 of 4, because we were told that the signal level was actually 4. So log base 2 of 4 will be 2, right? Because it's 2 raised to the power 2. That is 4. If 2 raised to the power 0 is 1, 2 raised to the power 1 is 2. Obviously, 2 raised to the power 2 will be 4, which is 2 times 2, right? 4. Great. So it's 4 times 3,000, which will give you um, 12. Wait, no. Yeah, 2,000 times. So that would be 6,000. 6,000 times times 2 will be 12,000 bits per second. I hope I got that right. Log base 2 of 4 is 2. So 2 times 3,000 is 6,000. Yes, that's correct. So 6,000 times 2,000 will be 12,000 bits per second. That will give you the bit rate. So let's go through and see if that's correct. So this was a question, right? We had 4 signal levels, and using the uh, same noiseless channel with the same bandwidth, the bit rate should obviously be correct. So that's about right. Yeah. So log base 2 of 4 is 2. 2 times 3,000 is 6,000. 6,000 times 2 is 12,000 bits per second. So from the look of it, you can tell that by increasing the signal level, if you look at the 2 questions that we had, if you did increase so if I look at this one, if we're to be increasing the uh, signal level, obviously you're going to increase um, you're going to be increasing the bit rates, and that usually tends to create, in a way, create uh, reliability issues within a given system, because the higher bit rates that you have um, can lead to some of the signals, some of the bits uh, getting lost in transmission because they have a higher bit rate. Especially if the system cannot accommodate it with the given bandwidth. So if you're gonna be having if you're gonna be getting well, if you're dealing with a system with